So just as a reminder, with predicate logic, we will be able to express real-life situations and properties in a much more elaborate way. Okay, so we won't limit ourselves to symbols denoting large concepts. Okay, we're not gonna use only one symbol P or Q to denote a whole sentence where we have a subject, a verb, and a complement, stuff like that. Okay, so for example, someone like Rachel reads a book. Okay, so we may use the verb as a predicate. Typically, we do this, okay, to say there is a relation called read between the subject, which is Rachel, and another object, which is the book, okay? X loves Y. We can say that today the temperature is 9, maybe, okay? And it feels like 4, okay? So we can combine concepts using conjunctions and so on and so forth. To do so, we agreed last time to use capital letter symbols. We can use whole words if it's more convenient, easier to read for us, such as PMR and so on and so forth. We are going to use small case letters such as X, Y, Z to denote variables that range over a certain domain. Okay, so X could be, so if you say read X, Y, X would range over the domain of all the readers, persons that you know, and Y ranges over the domain of all the books in this case. Okay, in this case, when you apply those functions, predicates, over those variables, you will get either a true or false out of it. Okay, so they give you what we call propositional functions. They map variables to truth values, true or false. But to say read X, Y, it doesn't have a meaning, or we cannot yet evaluate it unless we add a quantifier beside it. Okay, so we can say for every X, read X, Harry Potter, and then in this case we can say whether it's true or not, to just because it expresses that everyone has read that book. Okay, so let's jump to the new part. Okay, so we discussed all those details last time and we considered multiple examples. Today we're gonna check how to express actually how to translate from English to logic. Okay, so this must pass through one first step where you define your predicates. Okay, and there are plenty of different ways of defining your predicate. Okay, and you have to define your variables, the domains over which those variables range. Okay, so typically this is how you define your variables. So you need the predicates, the domains, and afterwards you can define your first order predicate logic formulas. Okay, let's consider one example. Translate the following sentence into predicate logic. Every student in this class has taken a course in Java. So can you give it a try? Okay, so I have this sentence here and we would like to interpret it. Yeah, please. Sorry? Yeah, okay, so let S belong to this capital student set. Okay, so the set which is the set of students in this class. Okay, good. Let J be a predicate such that such that J of S is true. Okay, if and only if S has taken a Java class or Java course. Do you agree? Okay, good. Now, how can we express this property? Yeah, so for every S, we have J of S. Do you agree on this? So I agree with you that we have this uh, trick here, like because we are defining the predicate. So you can define it in whatever way that's convenient to you to say things shortly, okay, in this way. So, and now this is a reading of that sentence. So for every, let's recompose it using our definitions. So for every student S in this class, that student has taken a course in Java. So it's exactly the same original sentence, okay? But let's discuss it furthermore. So what if uh, your variable S, so if you're, it depends really on your problem. So here we have one single sentence, but usually in exercises or in real life settings, you have multiple properties, okay? That have to do with something with each other. For example, the example from last time about broadcast news and the situation of the weather. Okay, so we had the news itself, the news source, and the news itself as two different components. Okay, so we should have introduced the fact that it was said by BBC or by CNN. Okay, so imagine that you have other sentences talking about students from other classes. Okay, so imagine that you have other sentences talking about properties, facts about other students coming from other classes. Then in this case, you may, to be able to express them all of them at the same time using the same domains for your variables, then you may need to make a certain generalization of your sets instead of focusing only on students of this class. You will make the fact whether the student belongs to this class or not a property, another predicate. Okay, you may introduce another predicate to express the fact that the student belongs to this class or the student belongs to the 207 class and so on and so forth. Okay, and you make your domain, your origin domain, the set of all students from all the classes. Okay, like the students at AUB, let's say. Okay, so suppose we need to do this at a certain moment. So how can we re-express our sentence above? So let us now, this is version number 2. Let us belong to, let's call it students at AUB, okay? So set of all students registered at AUB. Okay, I'm sorry for my, like, I'm writing on a vertically on the screen. So in this case, let's make J the same. Okay, so J of S is true if and only if S has taken a Java course. Okay, we still need to express something. If I say now for every S J of S, then it means that all the students at AUB have taken a course in Java. And this is not the exactly same meaning as the original sentence. Okay, so what do we need to further tune my final sentence? Okay, so we need another predicate to express the fact that one or some of those students have taken this class actually, okay, or registered in this class particularly. So let's call it C, okay, to express the fact that student S is in this class. Okay, is it fine? And now, of course, if we say for every S, J of S, it's not true anymore, okay? Because this means that all the students at AUB have taken a Java course. So how can we say that every student in this class has taken Java course. So for every S, I have a first suggestion. For every S, C of S implies J of S. Okay. Do I need to put parentheses here? Yeah. Yes, because by default, the quantifiers absorb the term that comes after them. So, okay. And in this case, if I don't put parentheses, then you should read it as follows. For every S, C of S, so all the students in AUE have taken this course. And this fact implies that J of S for a certain S that is not bound to any quantifier, which is not good. Okay, this sentence alone without a quantifier does not make a sense. So please, you have to add the parentheses. Okay, and I think this is what you meant. Okay, so for every student, if it happens that that student is in this class, then that student has taken a Java course. Okay, don't you think that this is fidel to the original sentence? Yes, please. It's not a well-formed sentence. The first part of it, so without the parentheses, the first part of it for every S, C of S is well-formed sentence, and it means every student at the university is in this class, which is not really true. And this implies J of S. J of S for what? For which S? Okay, this S won't be within the scope of that quantifier anymore. Okay, so this is why without the parentheses, it's not even well-founded. Okay. Maybe if you put again for every here, then you will have a well-formed sentence, but it means something completely unexpected. All this student, if all this, it becomes an implication, so it's a conditional. If it happens that all the students at AUB have taken this class, then it means, then in this case, all the students at AUB have taken a course in Java. So it could be true, okay? It's just a conditional. Maybe you have no student who has registered ever in this course, in this case, okay? But the original sentence says, every student in this class particularly have taken a certain course in Java, okay? So this is the best description for this. Do you have alternatives to this one? Do you have other suggestions that you would like to discuss? Yes, okay, so the pitfall that comes with this is this one. So for every student, so if actually the student has registered this course and that student has taken Java course. What do you think about how would you read this one given the definition of the predicates? Okay, so it's too much concern. Like now you are making this assumption that everyone at AUB has taken a course, has registered this course, and has taken a course in Java. Okay, so which is not true at all. Okay, if you say that there exists, then this is also a different reading. Okay, so you may say that there exists at least one student who has registered this course and taken a class and has taken a course in Java, but this is different from the meaning of the original sentence, okay? Here, what we meant that every student in this class, everyone, okay? Not only some of them, okay? So by the way, if this class is empty, this sentence is still true. Okay, once again, if the domain is equal to the empty set, then you can always pretend that all of them have a certain property, any property you want, okay, because the first part is false. Yeah, so you want to say that there are some students who, or at least one, who has taken a Java course and who is registered in this class. This is what you meant, okay? Yep, but again, this means that you are sure that there is at least one student who has registered this class and who has taken a course in Java, okay? This is not what is meant by the original sentence, okay? In the original sentence, for every student registered in this course, they could be none, okay? They have taken a Java course. Here you are assuming a different meaning. So according to the sentence, number 3 here, We are sure that there are some students in this course and they have taken a Java course, okay? But we are not sure that all of them have taken a Java course. So we have two different problems, okay? Now you are imposing, you are letting us imagine that the class is not empty. There must be some students in the class. At least one of them or some of them, they have taken a Java course, but it's not the case that all of them, okay? It does not mean that it's necessarily the case that all of them didn't take a Java course. No, I agree with you. Okay, so we cannot say this anymore. All of them did not take a Java course. No. Okay, but we are not sure yet that all of them have taken a Java course. Okay, this sentence does not imply this. Okay, you are just sure that some of them are registered in this class and they have. Yes. Yes, this is what we have done here. You want to use an application with the there exist. Ah. Um, as alone is just it's not a fact. As it's just a variable that ranges over the set of students. Okay, but as is equal to Sam is a fact that could be evaluated to true or false. Okay, no, it's not a statement. A student as, but you don't have any property about it. Okay, and even if you put a predicate around it, C of S, you still need a quantifier to say whether this is one of the students or all of the students have this property. Okay. Okay. Uh, yeah. This is hard coded inside the literal S itself. Okay. We can do this, and you need to do this. You need to do this just in case in your problem you are handling elements from that are students at IUB and that are not student at IUB. Then you need such a predicate to further specify, as we did with this predicate C of S. So once we enlarged the scope of or the domain of our variable, instead of just considering the students that are registered in this course, when we enlarged the domain scope to consider all the students who are registered at IUB, then we needed a predicate to further specify it. So I'm just letting you know that you need this A of S to tell that this element S, okay, is a student at IUB. I agree with you, okay? But now we have to make a version number 3, so why not? What did you want to continue with this? Yeah. Sure. So, but in this case, if S belongs to a universal set, like let's say all Lebanese citizens or all people on earth or okay, something like that, like just a bigger or all students in Lebanon, okay, some bigger set, okay. So I totally agree with you in this case. You need to have this, okay. What the parenthesis around the and is optional, and we need a parenthesis around this implication, okay. So I totally agree with you. You can make this version number 3 if you're dealing with elements or with the students from AUB from other institutions, then you need to further specify whether that element is particularly an element in who is registered at IUB, okay, who meet this property. So if they meet this property and you further tune it to say, I'm not talking about all of them, I'm just talking about the subset of them, those who registered this course, then in this case, J of S. So by the way, this tuning um, has been done in this version here, okay? And it was not required at all with this version because my elements S, all of them in this first version, uh, met this property implicitly. I'm just talking about students who are registered in this class, okay? I was talking about them. So it's implicit as if the property was true, and true implies J of S, okay? Okay, good. Any other suggestions, discussions? Yes, please. Yeah, please. Ah, absolutely. Thank you. So now you're suggesting like a certain different way. Okay, you're gonna be playing on the duality of for every and that exists using negations. Okay, so I think you're on the right through. So which domain would you like to play with? The second one, the students at IUB. Okay, so you want to say that it's not the case that you can find a student. Okay, such that that student is registered in this course, but okay, that student is not has not taken a Java course. Okay, and parentheses around them. I totally agree with you. Okay, so this one is for that one, and this one is for that one. Okay, to negate all of this. Okay, so I agree with you, and you will see, guys, that this is the dual. Okay, the negation of the well, this whole sentence is equivalent to the one that you have here, to the first sentence in version number 2. Okay, so it's equivalent to it. Okay, but this means that the sentence in version number 2 is equal to the negation to the one inside the triangle parenthesis. Okay, so if you can find a student, and we're gonna, this is very important, we're gonna use this to prove or typically to disapprove a certain property in mathematics. Okay, it should give me a certain theorem. All the integers have that property. Okay, and if I'm not sure that this property is really true, I have to refute it. I have to show you that it's not the case that I can find blah 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 blah. Okay, so okay, or to refute it simply, I can show you that I can find one element such that that element has that original property, yet it does not have the conclusion property. Okay, and then I can refute your theorem. Is it? Yeah. Sorry, the negation of. Yeah, this one I can find a student such that that student is registered in this course. Yet, yeah. Which one? This one. Um, you mean the negation? Yes. Okay. So the complete discussion about this example is as follows. You will see that the negation flips the quantifier. If you cannot find any, if it is not the case that you can find someone, so you cannot find any, then it means that all of them do not have that property. Okay. So it's really nice to see. Like we are jumping to a part in the next deck of slides, but it's completely fine. We can learn it from now. The effect of the negation is that it's gonna flip the quantifier, and it jumps inside the quantifier scope. Okay, to negate the internal of this problem. Okay, so on a side note, let's do it on a side note. If you are saying I cannot find any student or any x with that property p of x, okay? If you are saying this, then semantically, what you're saying that actually, if it is really the case, then this is logically equivalent to the case where all of the x's do not have p of x. If you're not able to find any x with that property p of x, then it means that all your x's do not meet that property x. Okay, I cannot find any student here who can swim, so I cannot find anyone who is able to swim. Then it means that all of the students are not able to swim. Okay, okay, so it's quite intuitive. So do you see it? To get it inside, you flip the quantifier and you keep the negation inside. Please don't forget to do this. Okay, you keep the negation inside. And if you apply it here, you will see the magic. You will see that it's 100% technically, without even thinking about it. It's equivalent to the first formula in version number 2. Let's do it. So this becomes equivalent to, for every student S, it's not the case that you have C of S and not j of s at the same time. So it means that for every student, it's either not c of s. Okay, now we can apply De Morgan's law because we have a negation and a conjunction. Okay, so it's traditional propositional logic. So it's not cs or not js. Okay, but not js is equal to js logically. Okay, so this is why you have for every student s, it's not cs or js, which is the implication. Okay, so we have a parenthesis here, we have a parenthesis there, and now this is equivalent to for every s, c of s implies j of s. Okay, it's fine. I'm positively surprised because you're jumping to the advanced part of this course. Yes. Yeah. Yes. Yes. The third line. Yeah. So for every student S, so if you check any student, they either didn't register at IUB, once again, because we have version 2, so we have this scope. So every student at IUB, they either did not register this course, or necessarily they would have taken the Java course. Okay? Or I can also say it as follows. It's not the case that they did not take any Java course. Okay? It's not. Okay? It's hard to say, but yeah, not it's equivalent to not p is equivalent to p itself. Okay, so for every student, it's either the case that they didn't register this course, or else they necessarily must have taken a Java course, which is the definition of implication. Yes. Yeah. Yeah. Sure. No. This. No. Why not? With the implication, you can have the premise and the conclusion true at the same time. Why not? So, actually, even in terms of disjunction, when someone has taken a Java course, okay, and did not register this course, is it a big deal? In our original sentence, we are just saying that the implication why. So just in case you have clouds and it does not rain, it's not a big deal, okay? So you may have both, okay? But otherwise, just in case this one is true, so its negation is false, then necessarily you must have that part, okay? Okay. It's always a good exercise to rediscover the implication, okay? Good. So let's get back to the slides, and you will see all those details inside the slides, okay? Well, the existential operator is just the dual. So I think now we are ready to understand this one a bit easily. If we consider the set of all students, then we can say, in this class, then we can say that there is a student in this class who has taken a Java course. But if you consider the set of all the students, then you need to refine it with this predicate, okay? There exists a student at IUB who has taken this course and or has registered for this class and who has taken a Java course, okay? So this is the translation of some students in this class have taken a course in Java. Okay, so once again, it's the dual. Since we talked about the negation, can you give me this sentence and its equivalent for every counterpart? Can you give me the logically equivalent sentence to this one, but using the for every quantifier? I have two suggestions. You may need a negation at first, okay? It's not the case that for every x, not this one, okay? Okay, so well, like let's do it together. So the original sentence was you can find some x's such that if x satisfies so actually such that X satisfies S and satisfies J, okay? So X has those two properties, okay? This is equivalent to the case that it's not the case that for every X, we don't have this property, okay? Um, what did you mean? So, hmm. Um, so let's consider an easier property. Let's say originally we were saying that there are some elements such that they know how to swim, okay? Okay. You are suggesting that we can rewrite it as follows. It's not the case that all of them know how to swim, okay? So, well, when you are sure that it's not the case that all of them know how to swim, okay? This is equivalent to you saying that you're sure that there is someone who does not know how to swim, okay? So let me put it this way. So this part here is equivalent to you are sure that there is someone who does not know how to swim, okay? And this is completely different from this fact. If you know that someone know how to swim, okay? So you just ask one of them going out of the class, do you know how to swim? He told you, yes, I know how to swim. So you cannot say that you knew about someone who does not know how to swim. This is a different fact. Maybe you know both of them. If you know this one and that one, okay, that some of them know how to swim, some of them does not know how to swim, then you are sure that it's not the case that all of them know how to swim, okay, and you are sure that well this one to the left is equivalent to it's not the case that all of them does not know how to swim, okay, which is a different meaning, okay, so if you know that some of them know how to swim, then you are sure that it's not the case that all of them does not know how to swim, okay, but you are not sure that all of them, for example, does know or does know how to swim, okay, it's not sufficient, okay, you need to ask more students, okay, so those two are equivalent. You may have both at the same time, okay, you may have the fact that some know how to swim and some others does not know how to swim, and you live fine with it, okay. Okay, the other cases, guys, are when uh, all of them know how to swim, okay. If you ask all of them and you check that they really know how to swim, then all that you are sure about, you can give me the challenge. Go and find me someone who does not know how to swim, and I won't be able to find it. So you are sure that I won't be able to find any student who does not know how to swim. Okay, so so this is the negation of the one to the right. Okay, second line. Okay, you see. Okay, so if you're sure that all of them know how to swim, then you know that I cannot find anyone who does not know how to swim. Okay, dually, so those are dual, different, and here they are different. So if you are sure that all of them does not know how to swim, well, this means that I cannot find anyone, okay, um, who, who can actually swim. Okay. So do you see the nice duality? Yes. Yeah. Uh, a very nice spotted idea. Okay. So this is a very nice question, guys. Please, Watch it, please. Your colleague is asking if you're sure that all of the students know how to swim, or like all of the axes know how to swim. So can we say that, this implies at least, so that you are sure that there exists is an element X such that as of X, so that students know how to swim. So actually, only when you are sure that the set of X's, the set of students, is not empty. So we still need that additional condition, okay? Technically, logically, and everything you want, okay? Okay. Sorry. Then you can say whatever you want about it, okay? I don't know, like I can give you some examples. Like I'm just thinking about awful examples. I don't want to say them, but okay. So about something that, okay, like all phantoms who are traveling in Beirut during the night are blank, okay, or white. So I can say whatever I want about them because, okay, so okay, and argue about them and speculate about them, okay, because they do not even exist at the first place, okay. So this does not imply that I can find a Casper who is white, okay, a phantom who is white, okay. Good. And if only Casper is white, I cannot say anything about all the other phantoms, okay? So if you're sure that there exists, then you cannot say that all of them. You're sure that it's not the case that all of them are not white, okay? Because you have Casper who is white, okay? So good. Um, so very nice questions. Okay, what about this one? Some student in this class has visited Mexico, so so the answer is already there. I'm sorry. So actually, you have to refine. Okay, so student in this class denoted by as of X and has visited Mexico as M of X. Every student in this class has visited Canada or Mexico. Every student in this class has visited Canada or Mexico. For which purpose? Two predicates. Okay. So let's do it here. It's happening. Yeah, good. Yep. So for every X, C of X implies this property, okay, which is itself a disjunction. It's either they visited Canada or they visited Mexico. Okay. Sorry. I'm sorry. Okay. I agree with you. So yeah. So according to the slides, I should use C here, and let's use S for the first one, a student in this class. Okay. Okay. But if I was defining the predicates, I can do whatever you want. If your set of elements, I totally agree with you. Thank you. If X belongs to the set of students in this class, okay, then I can say for every X, C of X or M of X. Okay, I totally agree with you. Okay, good. So what about the logical equivalence? I'm already talking about this. So they are logically equivalent if they are equivalent in terms of their logical evaluation. If they give you true for every X and for every possible assignment of truth values. Example, if you have for every X, P of X and the Q of X, then this means that for every X, P of X and for every X, Q of X, okay? This is the distributivity of the, for every quantifier over a conjunction. and it's always true. So you have some other logical equivalences that you have to prove in the practice exercises. Thinking about as conjunction and disjunctions, actually, this is important to prove equivalence in predicate logic. If you want to analyze to verify the example that you had on the last slide, then you had to unfold your quantified expression, okay? For every x, p of x means that you have the p of x1, the p of x2 for every element, okay? And since, so for example, for this sentence here, if you unfold it, then you have p of x1 and the q of x1. And you have p of x2 and the q of x2. And you have p of x for every x, okay, up to x number n. But since and is associative, then you can reorganize. You only have a big conjunction of plenty of conjunctions, okay? So you can reorganize those conjunctions in a certain way to isolate all of the p of xi on one hand. So we have p of x1 and p of x2 and p, okay? And q of x1 and the q of x, okay? The first one can be reconverted back to for every x p of x. And the second part can be reconverted into for every x q of x. And this is why we are able to prove the equivalence between those two different sentences. Okay, so you need this trick. It's slide number 15 and 16, but you will need it for, I think, the last exercise in the practice set. The for every is the dual meaning, okay? And this is why they work dually with the negation, okay? So if you are sure that some element x has the property of p of x, then you are sure that p of 1 or p of 2 or they have that property. Good. Even if the domains are infinite, you can still think of the quantifiers in this fashion. We can actually use a big cup, okay, a big V, capital V, as a conjunction operator to say that we have the big V of P of I or Xi for every I, okay? Okay, or just use the 3 dots to say for every element in the list. Okay, negating the quantified expressions, we have already talked about it. So they work dually. Actually, we have a very nice table. I can jump to it because we already discussed those cases. So if you are saying that it's not the case that you can find an element with that property, then it means that all the elements do not have that property. Okay, so all the elements do not have that property. I had a nice chat with one of your colleagues via email, so I will. He asked me about a couple of nice examples. I will also upload it on the forum on Moodle so that you can check it. And please feel free to ask such questions on the forum right away. It's not the case that all the students have that property. Okay, so it means that some of them do not have that property. Okay, so quite intuitive, and syntactically, they are very nice to play with. Like just you pass the negation downside, okay? You flip the quantifier, you keep the negation inside, and then you deal with it using De Morgan's law and other laws that you know about. Let's translate those sentences. So imagine that you have 3 different. Yes, sorry. Sorry. Yeah. In this case. Actually, when someone is telling you that it's not the case that all of them have the property, then you are sure that some of them do not have it. This is all that you are sure of, okay? If you are sure at the same time that some of them do not have, some of them have that property, it may happen, okay? You know one student who has this property P of X, you know about another student at least, or a couple of students who do not have that property. It might be the case. In this case, you may have at the same time, there exists X such that not P of X, and there are some X's such that it is P of X. This means dually that it's not the case that for every X, P of X, and it's not the case that for every X, not P of X. Okay? You may have both of them, no problem. Okay? They do not contradict each other. But you cannot say that what they really contradict each other. It's such examples, for example. When you tell me that you know someone with that property and you cannot find any element with that property. So, well, this is a contradiction, okay? Okay, because, well, this one is equivalent to all of them do not have this property. And this is, you will see when we will learn about, by Thursday maybe, when we learn about, yeah, I know. Yeah, I wanted just to tell you when you have a contradiction, okay? If you tell me that you can find certain elements with this property and you can find some other elements not having that property, then this is completely fine. Okay, we can live with it. It does not imply any contradiction. Okay, this is okay, but it's not always true. It's something. This one is always false. Okay, the first one. This one, it's it's satisfiable. Sometimes it depends. Okay, and this is equivalent to the case where it's not the case that all of your elements do not have the property, and it's not the case that all of your elements have this property. Okay, so this is satisfiable. It depends on your problem, the effective property. Okay, so it's sometimes satisfiable. Why not? Okay, good. Good. So, yeah, let's check those examples. So imagine you have a universal set of elements, weird elements, where you have some elements being flegels, some others being snurred, and some other elements being thingamabobs. Okay, anything. So in this case, we're going to use f of x, s of x, and t of x to denote those elements. Okay, you will see during the exercise that maybe some axes are flegels and snurred at the same time, or maybe being a snurred implies being a flegel at the same time. Okay, so for any concepts that you have in real life, you may get them back to concepts like those. So if I say that everything is a flegel, so imagine that in our real life settings, the word flegel means creatures. Okay, so everything is a creature. So for example, okay, so we can say for every x, in this case, f of x is true. Okay, good. Nothing is a snurd. Yes, this is version number 1. So for every x, it won't be the case that it's s of x. So s of x will be false. Okay, but dually, you can say that I cannot find any x that is snurred. Okay, that is s of x. Okay, good. It's fine. All of legals are snurds. Ah. So imagine like you have like I don't know, like all wolves are animals. Okay, so a certain subcategory of another one. Okay, so do you remember the when we denoted the implication using a set notation? So we have a bigger set of animals, and we have the wolves inside it. So every flegel is a snurd. It means that for every x, whenever you find that f of x is true, then s of x is necessarily true. Okay, good. Some flegels are thingamabobs. So you can find certain axes such that, and, okay, thank you. Okay, so we don't use an implication. What if we write, there are some elements for which f of x implies t of x. It's very important to get rid of this idea, to discuss it, I mean, and to discover that it's not a good idea to express this fact. So what about expressing it in this way? There are some axes such that if f of x, then t of x. What's the problem with this? Because, so what? Yeah. So I'm just saying in this case that there is someone, okay, I'm sure that there is a superhero here in this class who once exposed to, I don't know what kind of rays, okay, uh, electromagnetic rays, he will be activated and like become the king of this earth. Okay, so but what if no one has that like inner power in it? Okay, I'm just stating a rule. Okay, if any one of us is a superhero, he would invaded the world. Yeah, okay, I'm sure that such person exists, maybe all of us, okay, but because all of us, as long as we don't have that superhero property, then we won't be able to do that big thing. Okay, so the sentence has a meaning. Okay, has a meaning, but it's a very weak meaning. I'm just stating that there is someone who has this rule embedded in it. Okay, I can even like say it with a universal quantifier actually. Okay, and that rule won't be triggered unless this part is true. Okay, so it's quite weak in assumption as an assumption with respect to the universal quantifier rule. Okay, so at least with the universal quantifier, you are telling me something useful, that a rule that applies to anyone. Okay, if you eat well, you will sleep well, something like that. Okay, the general rule that I can apply to anyone. Okay, but here it's a even weaker meaning. Okay, I know someone who will have a superhero powers triggered once he does this or that. Then it's really not a very useful information. Okay, good. No snurd is a thingamabob. S of x implies not t of x for every x. Okay. Or dually, you can say that I cannot find any x that such that s of x and t of x are true at the same time. Okay, dual of the implication. Okay, so this is equivalent to for every x, not s of x and not t of x, or you can also say it as exactly as you said. For every x, s of x implies necessarily not t of x. Then I cannot find any snurd who is a thingamabob at the same time. Okay, very nice. If sorry, and if legal is a snurd, then it is also a thingamabob. So if you take any legal and you constrain to look at those who are snurds at the same time, then this implies okay T of X. Yeah. Okay. So any student at AUB and registered in this course, then he or she must have taken a Java course. Okay. The version number 3 suggested by your colleague. Good. We can use predicate logic, of course, as we did with propositional logic to express logical properties of systems. So imagine you have a mail system where every mail message larger than 1 megabyte will be compressed. And in that system, if a user is active, then at least one network link will be available. So how can you proceed with translating this? So we need to define our own predicates, variables, okay, and then out of them we can define those complex sentences. So what about a predicate to denote the size of a certain message? Okay, so we can consider capital M being set of all messages. Okay, so and M belonging to that set. We can use capital U, this set of users, okay? And network links also being, or an actually, link L to denote the set of network links, okay? So now let's define the predicates, okay? So the first one is needed to describe the size of a certain message, okay? So either we can say size, we take a message, we take a value, and we take a certain comparison operator greater than or less than. We can right away use the predicate larger than, okay? Message M and a size S, okay? Well, size belongs to the set of natural numbers, okay? So I don't need to specify it, okay? Or set of real numbers, real as you like, okay? So to say that M is larger than size, okay? You have also another fact about messages, whether they are compressed or not, okay? Something that evaluates to true or false. So if you consider a certain predicate called compressed that takes in just a message, it will yield either true or false, okay? So it's true if the message is compressed. We need also to denote the fact that a certain user is active or not. Okay, this is also a Boolean expression. So we can say active of U to say that U is active. Network link is available. We can also use available of L to say that a certain link is available or not. So we can say active of U. U is active. And available of link L to say that a certain link is active, available, sorry. Is it fine? Okay, and now I think you can define your sentence. So what about the first one? Every mail message larger than 1 megabyte will be compressed. Every mail message. Yeah, so we can write it here maybe. If larger than, okay, comma 1, okay, C of M, okay, compressed of M, okay, and this is true for every message M, okay, good. If a user is active, any user, if a certain user is active, if there is a U such that active of U, and now the implies is for this whole fact, okay? If you have a certain user that is active, then at least one network link will be available. So we are sure that there exists a certain network link L such that, yeah, that network link is available. Well, look, if the right-hand side of this if statement talked about the users too, okay, then at least one network link would be available for that user, okay? Then it means that my quantifier here to the right, to the left-hand side must also have this sentence to the right-hand side with it, okay? So if the sentence was something like, if a user is active, so it means for every user, if that user is active, then that user must have one link at least available for it, okay? But in this case, we would say LU because it really depends on the U itself, okay? It's a link that is available for that user. Okay, it could be something like this. Okay, but here the sentence is talking about two different facts. Okay, uh, like suppose you are in the doing hiking. If you can find this type of fungi, then you necessarily must find some bears. Okay, but the existence of the fungi is like two different facts. Okay, okay. But whenever you find a fungi, then you will see a bear beside it. Then it's the bear of that fungi. Okay. Yeah. Okay. So good. Um, so I think we're done with that. So they defined a certain predicate called as to say something about the status of the network, and the possible values of that status could be available, not available, I don't know, okay, busy, and so on. Okay, so once again, this shows you how flexible it is to define your predicate. So it really depends on your problem and where are you heading from this definition. Okay, good. Yeah, yeah. What could really matter is the relation between the link and the user who's using that link, stuff like that. Okay. So the number of parameters of a certain predicate. Okay. Good. So one quick overview on the next deck of slides before the most important part, which is inference in logic. How can we make conclusions in logic? So it's a technical part about nesting quantifiers, because until now, you may have noticed that we restricted ourselves to only one quantifier in a row on every sentence, okay? So, but what if we need to express facts like this one? For every x, you can find a y such that x plus y is equal to 0, okay? Well, is it the same as there exists an x such that for every y, x plus y is equal to 0? Okay, so we are expecting already that they are not interchangeable. Okay, it's not the same meaning. Okay, first of all, because sometimes x and y are playing different roles inside the predicate. Okay, so is the father x y? Is father x to y? So it's not the same as is father y to x. Okay. So, for example, you can say for any person, you can find parents, okay? But it's not the case that every parents have kids, okay? So it's so specifically with predicates which have an asymmetric relationship between the elements, you cannot flip the elements order at all, okay? But even if you're here, for example, x plus y is equal to 0, they are playing the same role. You can also say that y plus x is equal to 0. Okay, their sum is equal to 0. Okay. Nevertheless, there is a big difference between saying that no matter what value for x you choose, you can find a value for y such that their sum is equal to 0. So actually, y in this case would be the additive opposite of x. Okay, so minus x. Okay, but it's not the case that you can find one element, except maybe no, actually, no, you cannot find it. Okay, it's not multiplication. Okay, if it was multiplication, then you can also find one element which is 0, such that for every other element, if multiplied by it, their product will be equal to 0. Okay, so you can say it for multiplication, but you cannot say it for this property addition. So in this case, you have to be careful when you evaluate your expression. So by the way, you can see your property as a universal quantifier property, where the property Q of x is that you can find a certain element y such that P of xy is true. Okay, and this is why it's completely different when you swap or switch the position of the quantifiers. Okay, so the order really matters. So when you have this property, x plus y is equal to y plus x, I think for every element y, for every element x, this property is true. Okay, so given the set of real numbers. You agree? Okay, because plus is commutative. Okay, and for every y, for every x, p of xy is true once again because plus is commutative. If you could prove the first one, then you can prove the second one. Okay. But if you consider this statement, then you can say that for every x, you can find a y, and y is the additive opposite of x. But you cannot say that you can find y such that for every x, okay? Neither you can find an x such that for every y, p of xy holds, okay? It's not the case. So can I say for the, you can find a y, you can find a y for which for every x, it's not the case that p of xy. Can I say this? Okay, because there are actually there exists at least one x, which is the minus y. Okay, for which this property holds. Okay, so I cannot refute its negation either. Okay, so it's simply this one is not true neither for p of xy nor for not p of xy. Okay, maybe all that we can say for a certain y, you can find a certain x such that this property holds. And of course, you can find other axes such that this property does not hold. Okay, so this joins our discussion early this morning. Okay, so sometimes you can find a couple of values for which the property holds, and you can find other couple of values for which the property does not hold. Yes, you have. Okay. Yes, please. Uh, yes. Okay, so you have the same quantifier up to a certain, so as long as it's the same quantifier, then yeah, okay. Um, so there is a type of bees for which there is a type of flowers, okay. Or there is a type of flower for which there is a type of bees, okay. It's kind of the same, okay. Yeah, although you might be interested in putting the accent or on focusing on the rather the existence of those bees. Okay, but technically speaking, it does not make a difference. Okay, but when you have an existential plus a universal quantifier, you cannot swap them at all. Okay, I think I'm gonna stop this slide. We shall continue next time and be ready for the new interesting part about inference in logic. Okay, thank you very much.